Okay, so have you ever noticed how you can sometimes just tell it's going to rain? Like the sky's got that certain look, the air feels kind of heavy. You don't even need to check a weather app to have a good
Yeah.
guess, right?
Yeah,
Yeah.
totally.
What got me thinking, what if we could do that with the stock market? Like, what if there were signs, patterns that could, like, tip us off about a crash?
Yeah.
Just like those rain clouds.
It's a fascinating thought. And it's what makes the idea of using math to predict financial turbulence so intriguing.
Yeah, because let's face it, everyone wants to know if a crash is coming.
Exactly. And, for a long time, the traditional way to try and figure that out was to look at how stock prices relate to each other correlations. But the thing is, during a crash, those relationships, they can go totally haywire. It's like trying to predict an earthquake by just looking at how the ground usually vibrates. You know, not so reliable when things get really shaky.
Right, right. So that's where this topological data analysis comes in. This TDA, this research you sent. It's saying it can like spot those patterns, but not in the usual way.
Exactly.
So instead of listening for the earthquake rumbling, we're like looking for changes in the landscape.
That's a great way to put it. TDA is all about looking at the shape of the data, not just the numbers themselves.
Okay.
So imagine like you're looking at a map of the stock market. But instead of cities, we have these clusters of data points.
Okay.
And TDA lets us see how those clusters form, how they shift, even how they break apart over time.
So you're saying this point cloud idea, which sounded super complex when I first read it, it's what we're actually seeing in those figures from the paper,
Yes.
the ones that look like star charts.
Yes.
But instead of stars, each dot shows us how the market is shaped at a certain moment.
Precisely. Take figure 7, for example, which looks at the 2000 crash. Each dot there, it represents a specific combination of stock returns at a given time. And by looking at how those dots are clustered, TDA lets us see the market's overall shape and how it evolves.
So it's like we're watching a time-lapse video of the market structure, and TDA can help us like point out the moments when things start to look kind of ominous.
Exactly. The paper's topological tail dependence theory, it suggests that as we get closer to a crash, those data points, those stars on our chart, they start to cluster more tightly. It's like watching a storm cloud gather, The shape itself is telling us something significant is brewing.
And that's what we see in figures 11 through 16 with the 2008 and 2020 crash.
Yes.
It's like those calm, scattered dots, they suddenly become this dense, almost like, ominous clump. You can practically feel the tension just looking at it.
Exactly. That shift, that change in the data's shape, that's what TDA allows us to detect. And it's what traditional methods, which often just focus on individual data points or simple relationships, might miss.
Okay, so this is getting really interesting. But the big question is, did this TDA approach actually work? Like, were they able to use these shape-shifting patterns to predict the crashes?
That's the million-dollar question, right? And in this research, they really put TDA through its paces. They didn't just look at one type of financial model, no. They applied it to a whole bunch of them, from like the really simple to the super complex.
And they use real market data for this, right? Not just like made-up numbers.
Oh, absolutely. Real deal. They used data from the S&P 500, the Dow Jones, Russell 2000, the whole shebang. They really wanted to see if TDA could, make those models better at predicting in the real world.
Okay, enough with the buildup. What did they find? Did it actually help them see those crashes coming?
Well, no model is perfect.
Right.
It's like trying to predict exactly when a leaf will fall from a tree.
Right.
But what they found was really promising. Adding TDA consistently made the models more accurate, especially in those, nail-biting periods right before a crash.
Okay. So it's like having a better weather forecast. We might not know the exact minute that storm's going to hit, but at least we've got a better idea of when to grab our umbrellas.
Exactly.
But how much better were the predictions, though? Like, can you give us a sense of the impact?
Well, let's take the 2020 crash, for example, since that one's still pretty fresh in everyone's minds. The paper has a bunch of tables, but the main takeaway is when they added TDA to their models, those error rates, they went down significantly. It's like TDA allowed them to fine-tune their predictions, making them, much more reliable, especially during like those crazy market swings we saw in early 2020.
Okay, so it's not like TDA some kind of crystal ball.
Right.
But it's more like it gives us a stronger prescription and, to see those warning signs in the market a little more clearly.
Exactly. And like any new technology, there's always room to, make it better. As researchers, they get more data, they refine their TDA tools. Those predictions are probably going to become even more accurate.
That makes sense. But I have to admit, all this talk about point clouds and shapes, it's still a little abstract for me. Like, how does TDA actually work in practice? Do I need a PhD in math to understand it?
Not at all. Not at all. In a nutshell, TDA takes complex data, like all those stock returns we've been talking about, and it turns them into something we can actually visualize, like those star charts we were talking about earlier.
Right, those persistence diagrams, where each dot shows us a different shape in the data. But how do they even create those diagrams? It sounds incredibly complicated.
It's actually a very elegant process. Imagine like you're back in school and you've got a tub of Play-Doh, and you take these little bits of Play-Doh representing your data points and you place them on like a board.
Okay, I'm picturing it. Little mounds of Play-Doh, each one representing a different, like, moment in the stock market.
Yes. Now, imagine a tiny circular cookie cutter, and you start with a really small cutter. So small that it only goes around individual mounds of Play-Doh.
Okay, so each data point has its own little circle around it.
Exactly. But as you slowly increase the size of that cookie cutter, right, those circles grow and they start to overlap. They start connecting nearby mounds of Play-Doh.
So it's like those Venn diagrams we used to make, where the overlapping circles show the relationships between things.
You got it. And as the cookie cutter gets even bigger, those Play-Doh mounds, they merge together. They form all these different shapes. Some might be long and thin, others might be short and wide. And what TDA does is it tracks how those shapes change, how long they persist as that cookie cutter expands.
And that's what we see on those persistence diagrams, right?
Exactly.
Each dot represents a different shape.
Yes.
And its position on the diagram tells us how long it, like, lasted.
Exactly. The shapes that persist for a long time, the ones that are represented by dots further away from the diagonal on the diagram, those often represent the most significant patterns in the data.
Hmm.
It's like finding that hidden message amidst all the noise.
So when you see those star charts tightening up before a crash, what that really means is that certain shapes are becoming more persistent, like more dominant in the market data.
Precisely. It's like, imagine watching a dance floor where everyone's moving randomly, and then all of a sudden, this group forms, and they start dancing in sync. That shift in movement, that emergence of a coherent pattern, that's what TDA helps us detect in the financial markets.
That's such a great analogy.
Thank you.
But instead of dancers, we have stock returns. Instead of the dance floor, we've got, the entire global economy.
Exactly. And just like a good choreographer can spot those subtle changes in the dancer's movements, TDA helps us identify those subtle but potentially crucial shifts in the market structure.
So it's not just about, like, predicting the next crash. It's about understanding how the whole system works, the interconnectedness of it all.
That's the beauty of TDA. It provides a much more holistic view of the market, revealing those hidden connections, those hidden relationships that traditional methods might miss.
This is truly fascinating stuff. But if TDA can do all this for finance, what about other fields? Like, what are the potential applications beyond just the world of stocks and bonds? Yeah, it's like we've been talking about earthquakes and weather forecasts this whole time, but this shape analysis, it could apply to, like, all sorts of stuff. What else could we, like, understand better if we start thinking about the shapes of things?
You're exactly right. The potential applications of TDA, they go way beyond just finance. Think of, like, any system where you've got tons of data points and they're all interacting in these crazy complex ways.
Okay, so like social networks.
Yeah.
Millions of people all connected, sharing info, opinions. That's like a giant messy web.
Exactly. And TDA could help us map out all those connections, understand like how information spreads, how trends kind of bubble up, or even think about something like disease outbreaks. We've got so much data now, right? Travel patterns, genetic info, even like social media posts about people feeling sick. TDA could potentially help us see those early warning signs, those little shifts in the data that might tell us, uh-oh, something's about to happen. Wow. So it's like having this like superpowered microscope that can see patterns in, well, anything, not just the stock market.
Right.
But with all this talk about shapes and patterns and TDA, does this mean all those like old school ways of analyzing things, like looking at financial ratios or disease infection rates, are those becoming obsolete? Like, are we throwing those out the window? Not at all. I think of it more like those traditional methods, they're like looking at individual trees.
Okay.
While TDA, it gives us a view of the whole forest.
Oh.
Both are valuable and they work together, really.
So it's not about getting rid of the old tools. It's more like we're adding new ones to the toolbox.
Exactly.
And with PDA, we're not just like adding a new tool. It's like we're getting this whole new way of seeing the world, right?
Yes, it's like we've been trying to understand this really complex machine by just looking at each part in isolation. And now, TDA, it's like we've got the blueprint. It's showing us how all those pieces fit together to make the whole thing work.
And that's pretty powerful when you think about it. To see the bigger picture, right? To see those underlying patterns that like drive how things actually work. It's not just about like calling the next crash. It's about understanding the systems that like we live in, from the
Mhm.
stock market to, nature itself.
Yeah, and that's what makes this whole area of research so exciting. It's not just these little incremental improvements, it's like a fundamental shift in how we approach these big, complicated problems.
It's like we've walked into this whole new era of like exploration, and TDA is our map.
Oh,
So to everyone listening, if you're as fascinated by this as we are, I'd say go dive in, learn a little bit more about this TDA stuff. It's a pretty cool field. And hey, who knows? You might just stumble on the next groundbreaking use for this amazing tool.
absolutely. Remember, the world is full of hidden connections and patterns. They're just waiting to be discovered. And now we've got tools like TDA, so who knows what incredible insights are out there just waiting for us to uncover them.
That's the beauty of a deep dive like this. It kind of leaves you with more questions than answers.
Yeah.
But I think that's a good thing. It means we're on something big here, something that could change how we see the world.